You need to have critical thinking skills, so yes, that means logic and reasoning skills are necessary. You need to be persistent, so getting turned down is part of the job. So turn down for grants, turn down when you submit for a publication. So you have to be persistent as well. Creativity is an important skill. I feel like as a scientist, you really have to be able to think what could be going on in terms of, especially the field of biochemistry, because it's so abstract. So you have to have a creative mind to be able to pull that together. You need to be able to communicate. So a lot of times you will be asked to speak in front of a crowd, and so you have to be able to convey your information to other scientists and also to lay people. You need leadership skills. You're going to be a principal investigator of a particular grant, so you need to be able to have leadership skills in that. Being able to lead on a committee is important as well. Of course, time management, I mentioned that earlier as far as organization skills, so you need that as well. And social skills. So you will attend a lot of conferences, and you need to be able to network with people and be able to hopefully collaborate with those people.
So what you see here is the actual titration graph where you have your pH on the y-axis and the actual titrate, in this case sodium hydroxide, on the x-axis, okay? And so you should be able to determine the equivalence point on the graph. And so the equivalence point on the graph, let me just highlight, this area from top to bottom that's actually a straight vertical line for so long. The way you would find your equivalence point is actually you look kind of halfway between it. So if I were to kind of go over, if I were to do it correctly, maybe I would say that this pH for this one of the equivalence point would maybe be around 9. So again, you have to find where you have this long vertical line and you look kind of down the midway between that vertical line to find the pH of the equivalence point. So we know that we have an acid being analyzed because only the acid is present before the titrate starts. So how do we know that? Well, we know that because when you look at the graph, if I was to take and draw this line all the way through, we went from a lower pH, a pH 2, all the way up to a higher pH. And if you remember about pHs, pHs that are low are acidic, and pHs that are high are basic. So we started with a low pH. So that tells you that at the beginning of the reaction, you had only acid in this reaction before you added your base of sodium hydroxide. And then it continued to increase as you added more base, as seen by the volume of base being added, right? So at the point of this 25 milliliters of base being added, you get to the point where you have an equivalence point, okay? So is the acid being analyzed, though, a strong acid or weak acid? So look at the graph, and the question is the acid being analyzed a strong acid or a weak acid? The idea of, when you think of a strong acid, most people think of the one that's well known, and of course that's hydrochloric acid, okay? And so if you think of it in terms of hydrochloric acid, you would think that perhaps that particular pH would be even lower than a pH of 2. So that's one way you could say, well, maybe this isn't a strong acid, but perhaps a weak acid. But the other way to really be able to tell from the graph is, remember I told you that the pH of the equivalence point, when you're looking at it at this point, looks like it's falling at approximately 9. So if you have an equivalence point that end up being higher than at the neutralization, right, which pH at a neutralization reaction would be 7. So if it's higher than that and it falls into the basic range, that lets you know that what you are working with is called a weak acid. So I'll say that again. So we have an equivalence point where it's above 7 and falling right around 9. Because it's in the basic range, that means that this strong base reacted with a weak acid. So we did not use hydrochloric acid. Just to show for comparison, if you was using a strong acid with a strong base, the difference would be you would see it starting lower, closer to 0. All right, and I'm not going to do the dot, but I'm going to just show it like coming over. and somehow, kind of bear with me, showing somehow it reaches 7 and goes over. So in this case, it's a lot lower, right? So your pH of 7 lets you know that you have a strong acid reacting with a strong base. Okay, so keep that in mind. All right, so we'll continue with calculating, and so we're going to imagine that you're actually in the lab performing an experiment, and you're going to calculate the molarity based on the actual experiment that you did. So imagine you have potassium hydrogen phthalate, which is oftentimes called KHP. It has a molar mass of 204.2 grams per mole. The mass was measured at 0.551 grams using a standard balance and then placed into an Erlenmeyer flask, followed by adding 100 milliliters of distilled water from a graduated cylinder into the Erlenmeyer flask and then mix it. What must be added to the flask before officially beginning the experiment? So think back to everything we talked about with the other objectives. And before you can start this experiment, what must you add? An indicator. And remember that the most common indicator that you will use is called phenolphthalein. Okay? So now you've added your indicator, you mixed it, it's sitting up under the burette. And in the burette you have sodium hydroxide, which is the titrant. What reading is the burette going to be at when the burette is actually filled with the sodium hydroxide? Okay? So in this case, I want you to remember that the burette is this long 50 ml tube that has a little point at the end, right? So this is 50 ml. What will it actually read if you filled it up? And you should recall that it's going to actually read at 0 milliliters. So your burette reads backwards. So yes, it is filled to 50 milliliters, but your 50 ml mark is here, your 0 ml mark is here. So when you fill this up, all this space in between, you're actually starting your reading at 0 milliliters. Okay. And keep in mind when you add your indicator, you don't want to add too much or too little, so we usually say just add 2 to 3 drops. So now we're going to talk about what happens when the titration actually starts. The titration then starts by slowly adding the titrant. So remember, you filled it up, a total of 50 ml, but it was at the 0 ml mark with sodium hydroxide. So you added that titrant from the burette, then you let it start to run down so that it's going into the Erlenmeyer flask until the endpoint is reached. Once the endpoint is reached, the final volume reads 18.3 ml. How do you know that the endpoint has been reached? If you recall, you added an indicator called phenolphthalein, and that indicator will turn the solution a faint pink color, and that's how you know. All right? In order to know that it reached 18.3 ml, you would have to use your wonderful eyes to actually see that only 18.3 ml from the bottom, right? So your bottom has dropped. So if this is at the top and this is reading 0 and this is reading 50, right, you're going to measure how much did you lose here between this part. So remember, it came out through the bottom. Sometimes I know that's confusing. So we'll go down from this point of 0 down to 18.3, and at 18.3 is where it stops. And so that's how you know that that was the volume used. Okay? All right, so what is the molarity of the solution? So what do you have? If you remember, I'll put up, in case you forgot, you have the mass of the KHP. So the mass of KHP that you measured out on the balance was 0.551 grams. Okay? And the problem told you that the molar mass of KHP was 204.2 grams per mole. Okay? And then we just said that you read it, and the volume that was used was 18.3 milliliters, okay, which we know is 0.0183. Okay? So how can you calculate molarity from that? Well, you can start with your 0.551 grams, keep in mind your units. So if you have 204.2 grams per mole, you can put the 204.2 grams on the bottom, and that's what you have in 1 mole, okay? And remember now, I'm going to cancel units as I go. So we cancel that, and we end up with an answer that's 0.0027 moles of KHP. And you can actually take that and put it over the volume of 0.0183 liters. And just plug it into your calculator, and you should get an answer of 0.147 milliliters.